Okay, let's talk about some special applications of proportions. Now, in this one, we're going to talk about what are called direct proportions. Now, with direct proportions, you can also see the notes I'll upload on Canvas on this too. With a direct proportion, what you got to understand with a directly proportional relationship is as one amount increases, the other increases with it, okay? Or if it decreases, it decreases with it. Now, these are pretty simple problems. Again, just like any kind of story problem that we'll do in this section, it's about getting the right information in the right spot. So we look at this one. I got a story problem for us here. They say if a machine can produce 88 parts in 2 hours, how many can it produce in 3.5 hours? Okay, so with all these problems, we know they're going to be proportions. So what I always tell people to do is just draw two blank fractions. Now with this one, what I always tell people to find is, don't forget that these are ratios, right? And what's a ratio? A ratio is a comparison. So in this case, we kind of find what we're comparing. In this case, we're comparing parts to hours. Okay, those are the two amounts we're comparing. So what I always tell people to do, I mean, you can list the information off to the side. We got 88 parts, we got 2 hours, and we got 3.5 hours. So what I always tell people to do is find the comparison, like what goes together. Well, in this case, they compared 88 parts to 2 hours. So that's what's linked. And after you find that pair of information that's linked in a direct proportion, I just put those right over each other. 88 to 2. 88 parts is 2 hours. Okay, and what this does, now remember, this represents parts, and this down here is hours. Okay, now the reason I have you getting so descriptive in this is so you know where to put the other piece of information, because a lot of people on this one, they're like, okay, I can find the first comparison, okay, but what do I do with this third piece? Well, since we put this as parts over hours, since there's an equal sign here, the other side's got to be parts to hours. It can't be hours to parts. That wouldn't make any sense. So we got to put the 3.5 on the bottom here, and then we're trying to find some unknown amount. That's what we're trying to find, how many parts. So we're going to represent that with x. I mean, you can use p for parts, whatever. It doesn't matter what variable you use. You can pick whatever you want. You can put a smiley face there if you want to. I mean, it's whatever you choose. Okay, so now once you get to here, it should be business as usual. We just cross multiply. Take 88 times 3.5, and then 2 times x. So we get 2x equals, I'm going to cheat again, use my calculator here. Let's see, 88 times 3.5, 88 times 3.5. I think I did something wrong there. 88 times 3.5. There we go. That seems more right. 308. So we get 308, and then just like last time, or all the other problems we solve like this, divide by 2. So we get x equals 154. Okay, now with these ones, you've heard me say before, ask yourself if the answer is reasonable. Now we look at this answer makes sense because if we made 88 parts in 2 hours, we increased the time went up from 2 to 3.5, and our parts went up from 88 to 154. So that makes sense. It fits the direct relationship, As one amount goes up, the other goes up with it. And naturally, if one goes down, the other should go down with it, okay? So they rise and fall in unison. So be asking yourself that, because if you flip things around, the answer you get won't make sense. Our amount should go up. Okay, let's go to another example here. I got a couple problems we can look at. Let's see. Let's move that one down. Okay, so here's another kind of a simple direct relationship. If 1 gallon of paint covers 825 square feet, how much paint is needed to cover 2,640 square feet? Okay, so again, what's our comparison here? Find that first and then fill in the information. So in this case, they give us 1 gallon, 825 square feet, I'm going to express that way. 2,640 square feet. Okay, so just so you know, you can express square feet like that or like that. It's the same thing. We'll talk about that more when we get to the unit conversions in the next module. So we look at this one. What's the initial comparison? Well, they said 1 gallon is to this many square feet, so that's what's linked. Okay, so we put the 1, put the 825 on the bottom. Now the other piece of information they gave us, this 2,640, that's square feet. So I'm going to put this across from the 825 because notice square feet to square feet, gallons to gallons. Okay, you know, like the more organized you can make this for yourself, the better off you are. Okay, because a lot of people, you know, they want to try to make it harder than it actually is. Okay, overcomplicate things. Okay, so now we go ahead and multiply. So we do 1 times 2640. That'll give me 2640. Don't need the calculator for that one. X times 825. That gives me 825x. So then we just go ahead and divide both sides by 825. Okay, so we're left with x on this side. Sorry, these cancel out. Or they become 1. They don't really cancel out. Okay, so let's use our calculator on that one. Let's see, 2640 divided by 825. So we get 3.2. Let's write that down there. Let's see, so we got 3.2. Okay, and if you want to put gallons, like if you forget the units on these answers, I'm not going to dock you anything. I'm more concerned that you get the number, and I'm more concerned about this, the thought process, like how are you processing information. Okay, so we look at this one. So we got 3.2. That answer makes sense because if 1 gallon covers 825, and we increase the area by about 3, notice the gallons increase too. So again, like I was saying, you can ask yourself, you can ask yourself or troubleshoot these problems whether or not you got it right. Is as the feet, let's see, as the square feet went up, the gallons went up with it. So again, it just kind of proves our direct proportional relationship. Okay, let's go to the last one here. So this one is the same as the other problems. I just kind of gave it to you in a little bit different format. Okay, I'm being a little bit more secretive about how to set it up. So they said if the ratio of concentrate to water for a certain fertilizer is 1:32, how much water should be added to 7 ounces of concentrate? Okay, so there's some key words here. First and foremost, this 1:32, we know what that should be already, because when you have 1:32, we know that translates to 1/32. Okay, and then we got 7 ounces is the other piece of other number. But the other key word or key phrase right here to figure out what each of these numbers represents is right here. Concentrate to water. So that tells me when I see concentrate to water, that means it's concentrate over water. So this 1, that represents your concentrate. This one represents your water. Okay, so now if we go to the other side of the ratio, the other piece of information they gave us was 7 ounces of concentrate. So the 7's got to go on the top because it's concentrate, and the unknown is water. I mean, they asked us right here how much water should be added. Okay, so now we just do the same thing. Cross multiply. 7 times x is, or sorry, 1 times x is just x, and then we do 7 times 32. That'll give me what, 224? Okay, so now we look at this one. Notice I didn't have to do anything division-wise because when you just do 1 times x, you just get x. Okay, and it makes sense. You know, as our concentrate increases from 1 part to 7 parts, the water increased 7 times as much too, from 32 to 224. Okay, so again, you know, you look at direct relationship. As concentrate went up, water went up with it as well. And that's the direct relationship. As one increases, the other increases with it. Okay, so make sure you're asking yourself, does my answer make sense? Does it fit the context of the problem? Okay, and this answer does make sense. It fits because as this went up, that went up too.